Okay, for this video, I'm going to work under the assumption that you have a general knowledge of inverse functions and what one-to-one functions are. But we do know this about inverse functions. If I had a function f and its inverse and I looked at its t-chart, let's say it was a really simple little function with just three ordered pairs. And ones turned into fives, and twos turned into sevens, and threes turned into 15s. An inverse function just undoes the work of the first function. In other words, if the first function turns ones into fives, if we take the 5 to the inverse function, it would undo what was done, turn it back into a 1. Likewise, if 2's are turned into 7's, 7's get turned back into 2's, and 15's get turned back into 3's. So what we see is that our x values become our y values, and our y values become our x values. So it should come as no surprise that our process for finding inverse functions of equations like this would be to turn our y into an x and our x into a y. In other words, this y value, f of x is a y, of course, becomes x equals y minus 1 on 4. That gets us started finding our inverse function. So I solve this for y. 4 times x is y minus 1. Add 1 and I get y equals 4x plus 1. That's what y is, but really I'm going to name that as our inverse function. Why is it our inverse function? Because I changed x's and y's just like I changed x's and y's here. So this gets to be called f inverse of x. Inverse functions turn x's into y's and vice versa. Okay, show that the functions are inverse functions. To show that these things are inverse functions, if two functions are inverse functions, and I put something into f and turn around and put something into its inverse function, in this case g, I better end up with an x at the end. So I'm just going to show that either f of g of x or g of f of x, as I drew it over here, gets us back to x. We put in x, it changes it to something, maybe a star. We put the star in here, we've got to get back to x. So let's see. So f of g of or g of f of x would be g of x cubed plus 5. If we put that into g, we get the third root of, g is a factor that takes things and puts them right here, x cubed plus 5, and subtracts 5 from them under the radical. Well, this quickly becomes third root of x to the third, and that is x, and that's what we're hoping for. Now, we have learned that the composition, Fogg-Goff composition of functions is not commutative. However, I'm going to claim that if we have an indication that, yes, in fact, these appear to be inverses, it will be commutative. The book will say you need to now show that f of g of x becomes x, but I'm claiming that it absolutely will. If functions indicate to be inverses, then they are commutative. Okay, I'm going to approach this one from a graphic perspective at start. This is kind of a weird little deal. Let's think about that for a minute. If we rethink of this as f of x equals negative x squared plus 9, we ought to know exactly what the graph of this looks like. We are a parabola, but upside down and up 9. So we're up 9, but we're opening upside down. And I quickly realized that if I put 3 in here for x, I get 0. And if I put negative 3 in here for x, I get 0. I'm going to do that side in red. So I get a graph that looks something like this. And this. Now remember, we know that inverse functions just swap ordered pairs. In other words, 7, 2 becomes 2, 7. Or in this case, 0, 9 becomes 9, 0. And 0 or 3, 0 here becomes 0, 3. And that's the part connecting the blue graph, so I'm just going to draw that with a dotted, and I expect that's going to continue to look like this. And then the inverse of the red, 0, 9 becomes 9, 0. That's expected. And negative 3, 0 becomes 0, negative 3. Okay? So our blue flips onto our dotted blue as our red flips onto our dotted red. And one thing we should understand, x's become y's. The values that are on the y-axis over here that are positive flip to the positive x's. So we are flipping across the line y equals x. Okay? So if I go through the process of finding out if these are inverse functions, one way I could do it is let's find this inverse function. So this is just y equals negative x squared plus 9, or x squared, whoops, don't want to solve that yet. I need to swap, because of course inverse functions swap x's and y's. So x equals negative y squared plus 9. Solve for y. Y squared is negative x joins a plus 9. And then we take the square root and we get y equals, careful, plus or minus the square root of negative x plus 9. And we say, well, we had an issue with this all the way back at the very beginning, because this guy, my upside down parabola, does not pass the horizontal line test. It's not one-to-one. It does not have an inverse function, which is revealed right here in the solving for y. Its inverse isn't a function, or it was revealed graphically when our inverse of that graph didn't pass the vertical line test, if that makes sense. I hope it does. So that is why we have this lopping off of the graph, and we're only looking at that side of the graph. And remember, our blue transposed onto our blue dot, and that graph up here is the top portion, or the up part, of our algebraic inverse. That's why we end up with y equals positive square root negative x plus 9. Had we, up here, had this been less than or equal to 0, then we would be talking about the negative portion of the graph that is down here, the downward portion, because our red flipped onto our red. So that's a topic we're going to be talking about more as we move on. Okay, all we can do now is just intensify the algebra a little bit, show that these things are inverses, and I've got two choices. I could show that f of x, or f of g of x, is x, or I could take f of x and just find its inverse and hope it ends up being g of x. Both are worthy algebra pursuits. I'm going to go ahead and say this is y. I'm changing it to x equals, x's turn into y's. X's turn into y's. And I'm going to solve this equation for y, which seems okay on the front, but we've got two different y's. I'm going to cross multiply to get the y out of the denominator, and I get xy minus 2x equals y plus 3. I'm going to group my y's. Xy minus y equals add 2x joins a plus 3. I'm going to factor out a y. Y times x minus 1. That's good news. Now I have a single y finally. And I can divide away this factor. Y is 2x plus 3 on x minus 1. So there is an option. The other option, as I mentioned, is f of x, or f of g of x. Show that that equals 1. And I'm going to start that, but I'm going to leave that to the viewer to check this. That would be f of 2x plus 3 on x minus 1. F is a factory that puts things here and here, so that would be 2x plus 3 on x minus 1. There, still plus 3 on 2x plus 3 on x minus 1 minus 2. And that hopefully ends up equaling x. We'd have some cleaning up to do, and as I said, I'm going to leave that for the viewer. Okay, this is much like problem number 18, where we have a function that is clearly, by this time in your mathematical career, clearly not one-to-one. In fact, if I draw a picture of this thing, I know that this looks just like x squared, except it is to the left 3. So we have a vertex here. As I move 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll do that. As I move to the right 1, I go up 1. To the right 2, I go up 4. To the right 3, I'm up 9. And then when we have symmetry across here, so we have a graph that wants to look like x squared. It's just 3 to the left. Not one-to-one, of course, so we can lop this graph off. And on number 18, they lopped off a graph by only looking at the right side. So just to be different on this one, I'm going to lop off this graph and say we are only going to be interested in where x is less than or equal to -3. The cool thing on this is if we understand what graphs look like, we can do this with no algebra. Let's give that a shot. I'm not suggesting maybe you shouldn't do algebra, much like we did back on number 18, but I'm going to go ahead and do this without the aid of algebra here. And let's take a look at what happens here. So if I am only interested in, let's say, this blue portion of the graph, I'm going to plot its points, its inverse points. So -3, 0, our stopping point for the blue curve, would become 0, -3. And -4, 1 would become 1, -4. And -2, 4 would become, did I do that right? -4, 1 would become 1, -4. -5, excuse me, -5, 4 would become 4, -5, and so on. And our graph would look like this. And hopefully you can visualize that is a flip over the axis. Okay? So here's the beauty of it right now. We could go through the algebraic process, and I'll come back and do that, but let's take a look at this graph. Isn't this just a square root graph that is upside down and down 3? It's down 3 and it goes upside down rather than our typical square root graph that looks like this. So, square root graph. I'm claiming then, give myself a little bit of room here for the algebra. I'm claiming then we just need the equation of that square root graph that is upside down and down 3. I think that's what we're talking about if I use this as a constraint. Let's take a look. I'm going to set y equal to x and x equal to y. And I'm going to go ahead and solve this thing for y. I'm going to take the square root of both sides. Plus or minus x equals y plus 3. So I am looking at, or excuse me, plus or minus square root of x. That's important. Equals y plus 3, or y equals plus or minus x, subtract 3 away from the y. Once again, square root of x. Sorry. And so then we'd have to decide, am I the top part of the curve or am I the bottom part of the curve? And I think we need a graph to do that. But we see how this flips down to here. We're missing that top part of the curve. We're dealing with the bottom, so we're going to elect. But how nice is it to know what graphs look like and be able to build graphs? You want to avoid algebra? And even if you didn't want to avoid the algebra, you get to this point, you better know what the graph looks like to know which of those two you're going to choose. Awesome little problem. Okay, here we're supposed to find f inverse of g inverse of negative 3, and there's just a lot going on here. So I guess I'm going to find f inverse first. So I'm going to set y equal to x equal to y, and I'm going to solve this for y. I'm going to go y equals, I'm going to place my x and then see what I have to do. From y, I need to rescue 3 with addition, and then I need to rescue 8 with multiplication, and I get this. Or y equals, I guess I can call that f inverse of x equals 8x plus 24. And then for this guy, well, that's pretty easy. If I go x in place of y equals y in place of x, I get g inverse is third root of x. That's terrible. Let's do that again. G inverse is third root of x. So now I have a choice. Now I can build my f inverse of g inverse factory with x, or I can just put negative 3 into g, and I still need to find f inverse of third root of negative 3, and f inverse is a factory that does this. It takes 8 times the thing, in this case third root of negative 3, plus 24. That negative can come out, negative 8, third root of 3, plus 24. Okay, hope that was helpful, and stay tuned, more to come.